So this title is, of course, a play on recent topics that have been popularized in recent press, people talking about classes of users and classes of access. So what are the problems with wireless typically at NANOG? Well, they're all related to just fundamental natures of .11. The spec was written to not really address the 400 user load in one room that we experience. It was certainly meant for more of the 10, 15, 30 office users who are using an ERP application or telnet or something low bandwidth and low intensity. The limits that we experience here are mostly from packet per second limits inherent in each type of service within .11. Within .11b, you can really only support about 480, 479 transactions per second, and that would mean from any client to the AP or from an AP to a client, inclusive of all the acknowledgments. So this is a significant limit for any kind of small packet work, which seems pretty prevalent at NANOG given shell and SSH and everything else we use. It's slightly better with 11G. Definitely better with 11A. The true issue at hand is that with 11G and B compatibility enabled, the packet per second limit I've shown here does not become achieved. You don't get anywhere near it, perhaps a third of that. Still an improvement, but certainly not the solution to QoS or congestion at NANOG. The other issue with Wi-Fi or .11 in general is that every single frame transmitted over the air is positively acknowledged. So a good reception requires a statement of such. A missed reception is a non-statement of such. So that when you're actually working correctly, say in small ranges such as this, where we have 15, 20, 30 feet between yourself and every AP, we can be certain that 99 or better percent of the time we're going to have good reachability. Why consume resources to indicate something that's going to be a commonality? This was removed in .16 and several other protocols that are supposed to scale to several thousand nodes in the upstreams and downstreams of these systems. But this has not been thought about or really looked at implementing in .11 until very recently. The other issue at NANOG is that in the uplink direction, we typically do not see any facility until .11e is showing up of a way to control the emission of packets from client stations. Therefore, it's kind of a free-for-all around the constraints of the .11 MAC given detected station activities. But again, collisions are frequent. Collisions occur very, very often, and the resolution is lengthy. It's several measured in tens of microseconds. If we had a more structured protocol like .16, we wouldn't experience this in the first place. We would be essentially contention-free for the majority of the transactions. The other important mitigating factor is that at NANOG, even today, we've only sampled between 17 and 20% every few hours, by way of Bill Fenner's wonderful software, that we only really have a small portion using the best or most currently scalable protocol. That means that we have to really consider still the impact on B and G clients and what we do. So what happens if there is no QoS? Well, you all remember that, but we basically receive this. And we want to mitigate this as much as we can. So the goal of this is to really say yes, the two-tier model or kth tier model, which is what we're going to propose, is what we actually implement. So how did we improve the situation? Well, we took advantage of an 8-year-old RFC, which has finally been implemented in a lot of devices and finally works adequately well. So we feel it's mature enough. We deployed this. We are simply just matching the values that are available to us with disk-serve, IP precedence. We match these to various class of service levels in the access points themselves. To kind of help things out one step further for perhaps down-level SSH 1.5s, things that don't tag SSH packets as precedence 6 or low latency and type of service, we will mark 22 and 23 on ingress to the NANOG network as such. And we also mark perhaps unmarked IPsec as class selector 3, which is matched in other queues we'll show you later, as well as authentication headers, which we haven't seen any use of, but we felt important to match anyway. And in our case, again, as I mentioned, we don't have 2 tiers. We actually have 5 tiers at NANOG. So what did we do this year? We defined some simple classes: real-time, interactive, good, and best effort. We also matched for the real-time, of course, expedited forwarding, interactive for SSH, precedence 6, good, which we want to get through but can go behind real-time and interactive. We have AF31 and CS3. For best effort, we match anything that's DSCP tagged but not set to a class selector. In the policy map, we bind these classes together, and as you can see, cost 6, 5, 3, and 1 are where we're going to put these particular classes. Default goes to 0. Bind this to an interface. The 3 things I want to point out here are attaching the policy map at the top, A nice thing in general, unrelated to the policy map, is to set minimum speeds for the wireless interface. 5.5 megabits are basic rate. We don't support 2 or 1. At 5.5 megabits, we're still only servicing about 2 and some change megabits to a user at fairly low packet per second rate, perhaps fewer than 300. So that's our practical minimum. We don't want to go below this. And the packet retries command is also important in wireless, Cisco APs at least, and that is after maximum retransmissions have been experienced to a station, typically the station is sent a unicast deauthentication message, which some people on Windows clients will see as a wireless network disconnected. And that's probably not a good thing to exacerbate an already congested network. We fix that. On the router, we have a firewall config by Benson. And we are matching some other things to various classes. We have the freaking awesome class, which actually maps to the good cost map. And that is matching TCP SYN and SYN ACK, which we feel important to still support. And then once the session is established, we will allow TCP flow control to do its thing. We're also matching, as you can see, 22, 23, ESP, and AH to their appropriate classes. Now on the output side, rather on the input side, we attach these rewrite rules to match rather the firewall rules for the input and then output rewrite rules to implement the CS6 or PREC6 rather and CS3. Results are quite excellent, and as Todd and others might have mentioned and given in their various accolades, is that SSH is working nicely, which is what the predominant telltale of good network to us seems to be. The top trace route is ICMP responses from UDP probes from host yonder towards the laptop receiving maximum of .11b's abilities, say 4 and some change megabits on a Saturday morning or Sunday morning here. As you can see, the round trip latencies aren't huge to that station, but again, there is congestion in the FIFO out to that client. We have 102 milliseconds min, 151 milliseconds max through that simple sample. Previous hops are within a few hundred microseconds of each other. So we can be certain this is a good measurement. The bottom is TCP trace route on port 22 towards the exact same client seconds later, showing that we are getting the behavior we expect from that particular hop. We are seeing that 22 matched in the class map is getting to that station and a RST sent back in 14 to say 26 milliseconds with some reasonable determinism. So this is actually working. So looking at the APs, we can see what's actually being matched. We can say that in this particular access point I sampled this morning, very few people actually had any expedited forwarding traffic, meaning that I suspect very few folks using VoIP had it properly tagged ingress to us, or it was rewritten somewhere else, or nobody uses such things. Interactive, of course, is pretty prevalent, and we see, say, 40 to 100 kilobits on every AP. I didn't expect that much, but perhaps Pine and MUT are more popular than I thought. So good is matching all of the other things, AF31, CS3. We're seeing 100-something kilobits there. We're seeing, of course, best effort, which has the match of diffserv default, but not unlabeled. Some 100 kilobits, and the default is whatever trickles through, perhaps torrent traffic. In the firewall itself, on the firewall rules rather, on the Juniper, we are seeing a significant amount of the things we expect. We are seeing some IPsec matched. We are seeing only 1 or 2 telnet sessions a day, which is good. And SSH certainly is the runner-up, and behind that, everything else. So quickly, what's going on with this tier of software? Well, the issue at hand is that even though we have these classifications and we can make certain apps work really well, the rest of them compete for a very limited FIFO that you can't configure or customize as you may more complicated, more advanced router. That needs to be added perhaps in future revisions. Weighted fair queuing would be an excellent option here. We also cannot say to a class what the maximum bandwidth may be. The EF class may overrun any other classes. We would like to have a bandwidth maximum, just like any other Cisco product supports. And the default action, again, needs to be changed so that when stations do experience maximum retransmissions, they're not deauth or deauthenticated from the radio. Finally, cost values in the APs really don't just do what we would say would be priority queuing. We don't see them just simply for this packet if present ahead of others. We see them actually change the way the radio layer tries to retransmit in the case of loss. In the face of transactions in the air being currently underway, we will see that the back-off mechanisms are more aggressive, or less aggressive, for progressively more important classes of service. As you can see here, these CWIN, CWMIN, CWMAX numbers are tick marks in microseconds, if you will, for each priority queue in terms of how long we'll wait to first retransmit. For priority 0, we wait up to 15, as long as 1,023 megaseconds. And for 3 and on up, we will wait maybe as little as 3 microseconds, but only at maximum 7 microseconds before we try the packet completely again outside the radio layers. Again, you can see on the interface config below, we have the ability to rewrite these time windows, min and max, for each class. We left them default for this particular meeting. That's all. Thank you.